an IITG person promises only what he can deliver, and an IITG person delivers what he promises.
Welcome to this class of again computation of uniform flow. That we'll be discussing some more about computation of uniform flow in this class. We have already discussed in our last class how this resistance flow formula is used for computation of uniform flow, and as such we could see that for rectangular channel and for trapezoidal channel we need to go for iterative solution. Direct solution doesn't exist for this sort of channel. But when our channel is, say, wide rectangular channel, I mean, we can assume that the width of the channel is much larger than the depth of the channel, and for that channel we can have a direct solution for open channel uniform flow depth. Similarly, if our channel is a triangular one, for that sort of channel also we can have direct solution. Well, that way we did discuss some of the aspect, and then we found that when there is no direct solution, then we can either go for trial and error procedure using computer programming, or Excel sheet we can use, or we can go for graphical procedure. And that way then we were talking about, say, non-dimensional equation of uniform flow. That is, the uniform flow equation is basically having some dimension, and then the resistance parameter that we did use and is also in reality it is having some dimension, but we can derive that expression, or we can rather rewrite that expression in a form that this equation will not have dimension, and that will be having some advantage. We will be having some advantage in using that sort of equation, and by using those non-dimensional terms we can derive some approximate solution for computation of uniform flow. Well, let us proceed with that. We were talking about non-dimensional equation of open channel flow. Then let me take again the case of trapezoidal channel only, and just to recall what we did discuss in our last class regarding what is the dimension of n. Let me just keep it on the side, that the resistance coefficient, suppose Manning's n, its dimension, we can say dimension of Manning's n as L to the power minus 1 by 3 and t, that we did discuss. Dimension of n is equal to this one. Now with this, let me start with the equation of trapezoidal channel. Say we can write Q is equal to 1 by n, then area means say B plus ZYN into YN again I am writing for normal depth, and then to the power we can write 5 by 3, and then this perimeter B plus twice YN root over 1 plus Z square, and that to the power 2 by 3, and then SB to the power half. Well, so from that expression here, as we know that all these terms are having some dimension. Now if I write that y is the depth, and in place of depth y, if in place of depth yn, if I write a depth parameter, or we can make it non-dimensional if I divide it by say b, So I can call non-dimensional depth. I can write non-dimensional depth. So non-dimensional depth, how we are writing that? Yn by b. Suppose this we can write as Yn, capital Yn, which we can call as non-dimensional depth. Now in this equation, to have it in this form, let us divide this by b. Let us divide this by b, all Yn by b. So we can write, you can concentrate into the slide, that we can write it as q is equal to 1 by n. Then this part, if we divide by b, of course there it is a product, here y is also a product, so it will also have to be Yn by b, this Yn, and then this Yn also will have to be Yn by b. So let us divide this by b and this by b. So it will be 1 plus z into Yn by b, and then you will be having Yn by b. So in fact we have divided it by b square. So we need to, suppose if I keep this as to the power 5 by 3, so we have divided it by b, 2b here, b square, so we will have to multiply it by b square. So multiplying by b square, again that to the power 5 by 3 will be there. And similarly here, if I divide it by b, this will be say 1 plus twice Yn by b and root over 1 plus z square. Okay, and this one we have divided by b. So again, this is to the power 2 by 3. So here we will have to multiply it by b. So b to the power, it is just bringing out, so it will be 2 by 3. Okay, and then sb to the power half is there. Now if I write this equation in this form, that q, then n I am writing here, q dot n, and then sb to the power half I am writing here, sb to the power half I am writing here. Well, and this is equal to it will be 1 plus z, and this Yn by b I am writing as non-dimensional depth, say Yn, and then this Yn by b I am writing as non-dimensional depth Yn, capital Yn. This is to the power 5 by 3. Well, I will write the b later. Then here also I can write it like, say 1 plus 2 into capital Yn, non-dimensional depth, then 1 plus z square. This z is again the side slope of the trapezoidal channel, to the power 2 by 3. And then here we had b to the power, b square to the power 5 by 3, basically b to the power 10 by 3. Here we have b to the power 2 by 3. So if we just write it combining, then it will be b to the power 8 by 3. Well, from this, if we write that equation again, b to the power 8 by 3, I can just bring in this side, then it will be q dot n divided by b to the power 8 by 3 and sb to the power half. And this is equal to, now we can write on the right hand side whatever was there, that is 1 plus z yn and yn, all this area say 1 plus z, and this is capital Yn multiplied by capital Yn to the power 5 by 3, and then here we can write this expression 1 plus twice Yn root over 1 plus z square. So 1 plus twice Yn root over 1 plus z square to the power 2 by 3. Now this equation in fact is a non-dimensional form of the resistance formula, Manning's formula. We are basically coming with the Manning's formula here because n is there, and we are using the Manning's coefficient and other parameters also we are writing in this form. So it is basically a Manning's equation but in non-dimensional form. Well, now when we are saying non-dimensional form, then well, what about this particular part? This particular part, that we will have to be sure. Well, because that part we are sure that z is a slope, so this is a side slope, so it doesn't have any dimension. Then capital Yn, that we are already mentioning, it is a non-dimensional depth. So Yn, that is the Manning's, the normal depth Yn divided by b, means this is also a non-dimensional parameter, so it doesn't have any dimension. And as such, this right hand side we are sure, and this is 2, so this right hand side is having no dimension, that is confirmed. But what about this part, that is Qn b to the power 8 by 3 as b to the power half. Let us, if we check this thing, this we write normally as Qn, this we write as Qn, Q capital N, you can concentrate on the slide, and that is equal to, so 1 plus z into capital Yn into Yn to the power 5 by 3, 1 plus 2 into capital Yn root over 1 plus z square, this is to the power 2 by 3. And let me check just what is the dimension of this Qn, whether it is really dimensionless or not. Just if you put the dimension that Qn, this is say Qn b to the power 8 by 3 as b to the power half. Now dimension wise, if we put, what are the dimension of this? What are the dimension of this? So Q is discharge, so its dimension is meter cube per second. That means length dimension cube divided by t, meter cube per second, that is the time dimension. I can write t to the power minus 1. And as we did discuss already, well, first let me write here that b is equal to, say b means the bed width, so it is the length dimension, so L to the power 8 by 3, this is the dimension. And as we did discuss already that what can be the dimension of n, so dimension of n is L to the power minus 1 by 3 into t. So we can write that, say L to the power minus 1 by 3 and t, L to the power minus 1 by 3 and t. Okay. So this just straightway it is coming like that. It is L to the power by t to the power minus 1, then t to the power t, this is getting cancelled, and then this will become, if we see, it is L to the power 9 minus 1, so it is 8 by 3, and L to the power 8 by 3, this and that is getting cancelled, so ultimately it is 1. So that is non-dimensional, it implies that this is non-dimensional, it does not have any dimension. Okay. So that way this Qn we write as non-dimensional discharge. Well, now using this, just if we see that whether we can avoid those earlier conditions, that is the requirement of trial and error method for solving. Well, if we see this equation, though it is non-dimensional, then this capital Yn we again cannot separate out, it is remaining in the same form. So for the other constraint requirement, that is that it cannot be solved directly and we need to go for trial and error procedure, these are remaining as it is. Well, then we can go for some approximate direct solution that was given by Professor Barr, D.I.H. Barr and Das M.M. Das, that was given in 1986. Now, as I told that whether we today in today's context whether these sort of formula are having importance or not. Well, we have computer, so whether it is trial and error procedure or say a computer programming, we can go very quickly and we can have the solution. But still this formula has some importance. Why? Say even if we go by trial and error procedure, and if we use a computer program, then we need to put a initial value, that is first assumed value of normal depth we need to put, and that from that first assumed value it start iterating. And so if our first assumed value is suppose closer to the actual value, then we can reach our solution quickly. Of course, with the first computer this time difference may be very small, but still there is a difference, and we need to have that advantage. That's why I am discussing these equations. So that whenever we go for a computer programming for solving say normal depth, then at least we will be in a position to have the advantage of having this sort of approximate solution. Well, so this solution goes like this. They gave the solution for two cases, one is rectangular and one is trapezoidal channel. For rectangular solution, and this yn is nothing but that we have discussed non-dimensional depth yn by b. This is the actual uniform flow depth and divided by the bed width of the channel. And then this Qn, capital Qn, as we have already discussed, this capital Qn is nothing but capital Q into the Manning's roughness coefficient n, then divided by the bed slope to the power half and b to the power 8 by 3. So this Qn stands for that. Well, now what you can do, or what we can do, say if in a problem this Q is suppose given, this n is given, SB bed slope is given, then bed width B is given, we can first calculate what the Qn, that is what the non-dimensional discharge Qn. Having the value of non-dimensional discharge Qn, this equation you can see, this equation states that non-dimensional discharge Yn is equal to non-dimensional discharge Qn to the power 3 by 5 into 1 plus 0.855, then again Qn to the power 3 by 5. Equation is otherwise very straight and not that difficult also to keep in memory. Well, so if we calculate this Qn first and then put the value of Qn here and here, then we are directly getting the non-dimensional depth Yn. Now once we get the non-dimensional depth Yn, we can just get the actual normal depth by multiplying that non-dimensional depth Yn by b. So once we get Yn, then we can get small Yn means actual uniform flow depth, that is equal to non-dimensional depth Yn multiplied by the width of the channel. Well, so that way straight away we can get the value. And of course, as these formula or rather these formula are approximate solution, so always we can do one thing, or we should do one thing. Say first we are using these formula and we are getting a value of normal depth which is approximate value, and that approximate value always we put in the main formula. Main formula means the original formula that we are talking about. Say we can talk about this relation. Say in this relation we have got one Yn, then this Yn we should put here and we should check whether the discharge we are getting by using the approximate value of Yn, using this approximate value of Yn in these places, the discharge we are obtaining is really satisfying our required discharge or not. If the difference is very small, we can take that approximate solution, whatever we are getting as the correct. If suppose there are difference, say Q, it should have been 100, and by approximate formula whatever we have calculated with suppose putting the approximate value of yn here, whatever we are getting is not 100 but suppose 98, there is a error. Then we need to increase this by small amount, and then we are again doing iteration. But advantage is that now our actual discharge should be 100, we are getting a value of yn which is giving us 98, but without having that approximate value, if we start, we can be very far off from this actual required discharge, and then we will be requiring lot of trial and error. But here we can go very fast, and in fact for rectangular channel, I mean by using this formula we can get almost correct result, without much error. That can be even used directly also. But for trapezoidal channel the formula goes like this. For trapezoidal channel, you can see, concentrate in the this slide, that yn non-dimensional discharge is equal to again qn to the power 3 by 5, that is remaining same, and this is becoming 1 minus 0.69 divided by 1 plus 3 by qn to the power 0.35 and in multiplied by the z. So this equation is used for trapezoidal channel, and other procedure is same. I mean for trapezoidal channel also we can calculate the qn first, this non-dimensional depth, and non-dimensional discharge, sorry, and then we will be getting the non-dimensional depth. From that we will be getting the actual depth, and then in this formula of course there is some amount of error, always it is expected that some amount of error will be there, and so what we need to do, again we need to put it in the actual formula and we should check whether it is satisfying our condition or not. And if it is there will be some amount of difference, and then we need to reach the correct value by again moving as trial and error procedure. Well, so that way this approximate direct solution given by Bar and Das is useful in taking the initial value. Well, then with this very fundamental that we have discussed about the computation of uniform flow, now let us see how we can solve problem by using this formula. Well, let us take one problem and let us see how we can solve this. Well, to start with, we will not be taking very complex problem. First we will be taking a very simple sort of problem, and then we will gradually move on to complex problem. Well, so first problem, let us take it like that. A rectangular channel of 6 meter width and of bed width, you can concentrate to this slide, and of bed slope 6 into 10 to the power minus 3 is carrying a discharge of 5 meter cube per second. Well, Manning's coefficient can be considered as 0.014, and as we know that Manning's coefficient always we give some value, but depending on a natural channel, suppose it is whether it is man-made or natural, in a field situation when we go, then suppose based on some of the characteristic we can say that this Manning's roughness value should be this much, but in the entire channel reach you may find that there are differences. And suppose when we say that if it is a suppose channel of concrete lining, well, there may be a value for concrete lining that Manning's roughness value is suppose 0.014 or something like that. But again when we talk about concrete lining, this concrete surface may have different sort of roughness. A concrete surface made in a very polished way will be quite smooth, and a concrete surface made in a very raw way will be a little rough. So that way also there will be some differences in this value. And suppose we have made one concrete channel, and then with time it may happen that some erosion has occurred, some damage has occurred into the concrete channel, and then some part are just going away from the lining, and that way there may be some roughness induced. And so considering all those facts, this roughness, exact value of roughness is the quite a critical question, but still for our computational purpose we assume some value, and this is, say, Manning's coefficient can be considered as, say, 0.014, that is being given for this particular problem. And the question is that to avoid over flooding, what should be the minimum depth of the channel? Well, that means basically this question is of course stated like this or asked like this: to avoid over flooding. Say in a channel we know that this much discharge will be coming. It can be a canal or it can be a drains in the city, whatever it is. So say in that drain or suppose a irrigation canal, then suppose this much discharge will be coming, that is known to us. And bed slope is given as 6 into 10 to the power minus 3. And now always in the channel, when it will be in the real field, say we have very less chance or opportunity in our hand to change the bed slope, because if we need to change the bed slope we may have to go for a lot of cutting in the ground, or sometimes we may have to go for a lot of filling up of the ground. Then only we can make that we can afford to change the bed slope to some extent. So generally the naturally available slope, depending on the topography of that particular area, this sort of slopes are decided. And of course when we say that slope is this much, if it is a man-made channel, then we talk about that, okay, in the topography definitely there will be ups and downs, and in that channel if we want to just go by the average slope, then there will be somewhere some cutting, some filling anyway. Now in this channel when we are saying that the bed slope is this much, means it is the bed slope that we are defining, maybe average bed slope, which we get after some cutting, some filling up in the actual situation anyway. So this is the bed slope. Well, now this problem, now for that particular discharge, what we need to calculate here, that we need to avoid flooding. That means suppose if we calculate the normal depth of flow, that is a uniform flow depth, then we will be getting a depth of flow, and our depth of the section, suppose our normal depth is this much, then depth of the section should be little higher than the depth of the flow, so that this water will not overflow and will not the channel will not be flooded. Well, and so first, so far our knowledge so far is concerned that we can calculate the normal depth, and after calculating the normal depth we need to put some amount of excess freeboard. That we will be discussing in detail when we will be doing the topic of channel design. Lot of other things will be coming there, and canal design when we will be discussing, then we will be discussing that. But first what we can see that in this problem, if you just concentrate in the slide that we can solve, say we can first calculate it by approximate solution by bar and dash, and if we go by that, then we can write that yn by b. We are, rather than writing capital Yn, we can write it as yn by b, and this is equal to, this is basically nothing but the capital Yn what we were writing, and the non-dimensional discharge that we are writing directly as qn b to the power 8 by 3 as b to the power half to the power 3 by 5. Then we can write 1 plus 0.855. Then again this non-dimensional discharge qn b to the power 8 by 3 as b to the power half to the power, say, 3 by 5. Well, now we know that b value here, bed width of the channel, is given as, I think, 6 meter. Bed width of the channel is given as 6 meter. So if we take that 6 meter here, then we can write that yn by 6 is equal to Q is given as 5 meter cube per second, and then n value is given as 0.014, 6 to the power 8 by 3. SB is given as 0.006, means 6 into 10 to the power minus 3. So we can write it as 0.0006 to the power half to the power 3 by 5. Just writing the other part also, 0.855, and this part we can write the same value, 5 into 0.014, 6 to the power 8 by 3, then into 0.006 to the power half whole to the power 3 by 5. Okay. Now from that, the value of yn what we will be getting, that is equal to 0.3358 meter. I am writing this to the fourth decimal place, and then we are getting it as 0.3358 meter. Well, now of course this is an approximate solution. But for rectangular channel, this approximate solution is almost correct, but still we need to verify whether this is giving us the required peak charge or not. Then we know again the actual formula. If we use the actual relation, then we will have to write our original equation, that is Q is equal to area into velocity. So for rectangular channel we know that area is equal to Byn and velocity is equal to, say, 1 by n, writing Manning's equation, area and then perimeter B plus twice yn to the power 2 by 3, then base slope to the power half. Now here we do not know, we know the Q, but we cannot solve for this yn directly. So this value, if we put 0.3358 for this yn, after that writing this part, okay, we can simplify it first, then after writing this we can say the trial value of yn, we can go for trial. So trial yn is equal to, suppose, 0.3358, then we can see what the Q value is. Q value so if we put 0.3358, then we find little higher than this 5 meter cube, 5 point something, we are getting 5 point something, little higher than. And then I am not showing all the trial and error procedure, but for yn equal to 0.335, we are getting Q is approximately equal to 5 qmac, or 5 qmac or 6 qmac, what we were using, it is 5 qmac, okay, 5 meter cube per second, so that we are getting. So Q is approximately equal to 5 qmac for yn is equal to 0.335. This is exact solution. We may have to go for one more trial here, and that way we are getting it. So from this problem we can see that approximate formula can be used very well for rectangular channel. And once we get this yn, say 0.335, now what can be our size, actual size of the channel, this we can increase by some percentage, which we call as a freeboard, and then we can say that, okay, if our channel is greater than that value, then there will not be flooding. Well, that finer detail we will be going later, as I have told, but this is what the procedure, and that means a depth of the section, if I am asked, say depth of the section I can say as this is equal to 0.335 meter plus freeboard. Now as we have not discussed what should be the freeboard, right now I am keeping as freeboard only, so that way we can design the channel well. Similarly, we can have another problem. The basic idea is same, just to show how the numerical value can be little different and how the error can be little more in trapezoidal channel. Suppose if we talk about this particular problem, say a discharge of 60 qmac is flowing in a trapezoidal channel of 20 meter wide channel. Well, this is a little bigger size channel that is 20 meter wide, and then your discharge is also a little higher, say 60 meter cube per second, and then this has a side slope of 1:1. That means this is not rectangular and the side slope is 1:1. That is z value, small z value that we are writing, this is 1:1. That is z equal to 1. And bed slope is 1:10 to the power minus 4. Okay. And Manning's n is equal to 0.02. Manning's n is given as 0.02. Now, suppose simple question, find the normal depth, that is the depth of uniform flow, and check if the flow is supercritical and subcritical. If the flow is supercritical and subcritical, that we need to check. Okay. Well, what is supercritical, subcritical? To know that, of course, we need to go back to our I think second or third class, where we did discuss second or third class in open channel flow, where we classify the flow, and that is not that important right now. We will be just calculating whether it is supercritical or subcritical. But why I am putting this one here, to know whether it is supercritical and subcritical, first we need to know what is the flow depth, and to calculate the flow depth in uniform flow condition, we need to take help of uniform flow formula. Well, so if I just, you can concentrate into the slide. So if I go to the equation again, that approximate formula. Okay, I am not writing the approximate formula here. Already I have shown how the approximate formula can be written, and by approximate solution, I am just writing the value for approximate solution. The same procedure you can adopt, and then approximate solution gives us a value of yn is equal to 2.85 meter. That I am writing directly. For that, in fact, we are using the approximate formula what was given here, that formula. Using this formula, calculating this qn with the given q and given n value, given bed slope and given width of the channel, we are calculating this qn, and then z value we are using whatever is given. This z value is basically 1 because our slope is 1:1. So this z value we are using as 1, and then we are calculating this yn. So yn is again is equal to yn by b. So from that we are calculating this yn as yn is equal to capital Yn into b. So that yn what we are getting, this I am writing here directly, that this is the value of yn 2.85 by approximate formula of Bar and Das. And then saying so, if I write the direct equation or actual solution, say actual equation, if I write the actual equation that will be, say, q is equal to again a into v, and that we can write for trapezoidal channel as, say, 1 by n. Then area we can write as b plus zyn into yn, that whole to the power 5 by 3, and the perimeter we can write as b plus zyn into root over 1 plus, sorry, it is not z, it is twice yn into root over 1 plus z square, and whole to the power, say, 2 by 3, and sb to the power half sb to the power half. And here if we put this value of 2.85 in place of yn, then again we need to make trial value, trial y and q. So if I put this value first 2.5 discharge q trial depth and discharge. Okay, this if I put 2.85, then we find that the q what we are calculating, this is becoming less than the actual desired q. And what is our actual desired q is 20 meter cube sorry, it is I think 60 meter cube per second. Let me confirm, it is 60 meter cube per second. So it will be less, it is 60 meter cube per second. So what we can do in the next trial, we can increase it to some higher value. Suppose we are going to 3.00, we are going to 3.00. Then we will find that if you just put the value and if you try, then you will be finding that Q is becoming greater than 60 meter cube per second. And that way, if we carry out trial and error, then you will be finding that for a value of 2.93, for a value of 2.93, we get Q is approximately equal to 60 meter cube per second. Now, we may have some feeling that, well, what's the difference between this, say, 2.85 and 3 or 2.93? In fact, these are in say centimeter level, these are in millimeter level. What is that difference basically, or why we should be so careful about that? Why we should be so precise? See, if you use what the significance is, it's a big channel. It's a big channel about 20 meter width, and of course in nature we can have much bigger channel, like say in India, river Brahmaputra, river Ganga, if we talk about, then it can, the width goes to 2 kilometer, 3 kilometer, sometimes in Brahmaputra it goes even to 17 kilometer. So the highest width observed is 20 kilometer around. So that way it is though braided, in the flood time sometimes it flows covering everything. And in this sort of situation, so this difference of depth, when we calculate something, the difference of depth of even a centimeter matters a lot, because with that difference of depth, our flow discharge changes grossly, because the size of the channel is so large, that if our depth changes by small amount, the flow discharge changes a lot. And as you know that water is now becoming a very valuable, I mean it has a very high value, and it is said that world war will be there for water. So we should be very careful, and people are interested to know how much water is flowing. How much water means what is the quantity of water flowing. And if somehow our depth calculation, if we do computationally, if we do by our calculation, if our depth computation is erroneous, then our whole understanding about our discharge may go wrong. So that way, a small amount of depth variation is also significant when it is a very large channel. Of course, when it is a very narrow channel, say 2 meter, then or say 1 meter channel, like say irrigation canal or city drain, in those sort of channel or canal, say depth variation, if it is very small amount of depth variation in the millimeter level or centimeter level, will not matter. A centimeter level means I'm talking about millimeter level. Basically, say 10 millimeter or 5 millimeter, that is not making much difference. But in other cases, it will matter. And now, what is the advantage if we go by this approximate formula? Suppose as we are using this value 2.85, which is basically the approximate formula value, and from here we are starting. So with very limited iteration, we are arriving at a correct value. And in field condition, suppose we are going into the field and we need to have some approximate idea, then we can calculate this. We can use the advantage of this one, and then we can go for trial and error. Then we can see that what the actual value of yn should be. So that way we are calculating these things. Now the next question is to know that, so yn is suppose 2.93, and then next question is to whether the flow is subcritical or supercritical, Now if we just go back to our earlier class, then we remember that it depends on the Froude number. Of course, that we will be discussing in more detail when we will be discussing energy concept, and then when we will be discussing what is minimum specific energy, critical flow, that we will be just discussing in the next class. So that detail I am not going right now, but we know that a Froude number we calculate, this is equal to V by root over G D, where D is nothing but A by T. So once we know the depth, then we can calculate the D, and then V already we are calculating. Once we know the Q and the sectional area V, we can calculate, or we are otherwise calculating this V here also. So we can put that V value and we can put that root over GD value, and the Froude number value for that situation we are getting as 0.47. And if Froude number is less than 1, if Froude number is less than 1, then this sort of flow is called subcritical flow, and when Froude number is greater than 1, then it is supercritical, and when Froude number is equal to 1, then it is called critical flow. That we did discuss earlier also. Just here I am putting this point, that this knowing the whether flow is supercritical, subcritical, that has some other issues. That if it is subcritical flow, then the flow velocity will not be very high and the chance of erosion will be less, and if it is supercritical, flow velocity will be very high, chance of erosion will be high. So that sort of other things that we can derive from these answers. So that way we can solve this sort of problem. Well, then so sometimes without going for all those detailed calculation, we can have some other problem we can do easily, like that. Say a rectangular unlined channel of Manning's n equal to 0.03 was lined to improve its carrying capacity. So this is a very common practice. This is a very common practice that is adopted in many places. I mean, like for city also. Say we are having a drain which is suppose unlined, and then we are finding that in rainy period or in monsoon, this drain cannot carry the amount of water that is coming to the drain, and that's why the depth is increasing and it is getting over flooded, and that's why flood is having there. And so, and the water that is coming to the channel cannot move out quickly, and it is creating some sort of problem, water stagnation problem. So many a time we go for channel improvement. In fact, suppose in a channel, say this is the channel. In a channel, this we have some Q and some discharge is flowing, and then we want to drain out the water quickly, because if we cannot drain out the water quickly, here the water level will rise, and then when this is rising, suppose another sub channel is joining this channel, then what the water flowing here, that will also be affected, because once this water level rises, from here you will not be getting hydraulic gradient, here you will be having higher gradient, here less, so higher depth, here less, so flow will get retarded in this part also. So once in the main channel you have higher depth, then on the side channel also you will be having water with a slower flow, and then you can have flooding situation in this part also, as the water is not getting released quickly. And to avoid those situations, we try to improve the flow condition in the channel, here as well, everywhere. And then one option could have been very easy. Suppose we want to release it quickly. If we increase the slope, then of course we can release the water quickly. But as I was telling, that in actual condition, the slope cannot be increased, or slope cannot be, we cannot change the slope that easily. So normally we go for some other sort of devices, like that we try to improve the channel characteristic so that we can increase the flow. So this is a problem of that kind. Well, so a rectangular unlined channel of Manning's n equal to 0.03 was lined to improve its carrying capacity. Now Manning's n for the concrete line channel, suppose we are providing a concrete line, then concrete line channel is say 0.015, In the unlined channel, this Manning's roughness coefficient is 0.03, and the line canal it has become say 0.015. Now, what will be the percentage of increase in discharge? Okay, what will be the percentage of increase in discharge? Well, now in this problem, nothing is given. So, what is bed width and other things are not given. It is a rectangular channel. Just it is asked that what will be the percentage increase in discharge. Now, you can see that say for the first case, when our n is equal to 0.015. sorry, 0.03, when it is a 0.03, then we can just write that Q1 is equal to say 1 by n 0.03. Then A means we can write B into yn to the power 5 by 3, P B plus twice yn to the power 2 by 3, and SB to the power half. This is our say first discharge we are calculating. Well, then we are not calculating anything, we are just keeping it like that. Then say when we have in the second case, when n is improved, that is we are having concrete lining, then we can have Q2. We are having a different discharge 1.015, and of course the section of the channel is remaining same. So, by1 to the power 5 by 3 and b plus twice yn to the power 2 by 3. So, that part is not changing. Then sb to the power half. This is say equation 2. Now, our interest is to know that what will be the increase in the discharge. So, just by making 1 by 2, 1 divided by 2, we can have, that is Q1 by Q2 is equal to 1 by 0.03, other things remaining same, this will get cancelled, divided by 1 by 0.015. So, this indirectly implies that Q2, our second discharge, is equal to, if we just calculate it, this is just twice of, because this value is twice, so it will be 2 times of Q1, 2 times of Q1. That means, if I am asked that how much is the percentage of increase of the actual discharge, then you can say that it has increased by 100%. Earlier it was Q, now it is twice Q. Earlier it is Q1, that means now it is twice Q1, that means it has increased by 100%. So, increase in discharge is equal to 100%. Well, so that just show us directly that how by improving the channel characteristic, by providing lining, we can increase the discharge capacity or the carrying capacity of a channel, and we can have a better water management wherever is required. Well, now we are talking about roughness coefficient, but again in the when we were discussing about the computation also, then also we were just discussing compound channel, then we can see that this roughness coefficient n, when we are using, this is for a regular section we are talking about. This is rectangular, trapezoidal, or this sort of channel, maybe parabolic, exponential channel. But if it is a compound channel, like this, then as we know that as the depth of flow here is very less than depth of flow here, and this is very near to the bed, this is also very near to the bed and bank. I mean entire flow section, if we see, this is closer to the bed and the side, and this is far off from the side and from the bed. So, that way the roughness, because roughness is coming from basically bed and the side. So, roughness characteristic of this will be definitely different. This means suppose that we call as a flat plane, that we call as a flat plane, and that sort of flow will be there, and this is the main channel, this we call as a main channel. Okay. So the roughness value of the main channel, say n, if I write n, this is, and say this is nf, say roughness of the flat plane, and in the flat plane again, see this flat plane is normally do not get over flooded. Well, this will be flooded during monsoon period only, and as such when it is in a non-monsoon period, this is already having a lot of fertile soil element may be there, because during flood time it has left some of the fertile element, and then in the non-monsoon period flow is occurring here. So at that time the vegetation in this part get the opportunity to grow. So in the flat plane normally we will be having some vegetation, and that's why, as we know, that vegetation also influences the roughness characteristic. As such, the roughness value of that flat plane will be different. Well, so one point is clear, that n, if I talk in terms of Manning's roughness coefficient, this n here and here will be different. Now if we try to calculate the flow depth, if we try to calculate say what will be the discharge in this channel, then we need to know we need to calculate a equivalent Manning's n, and that is what we will be discussing just very briefly here. Of course we can go for a lot more discussion on this part. So different part of channel may have different roughness, and therefore it is necessary to go necessary to have an equivalent. We will call that Manning's constant, equivalent Manning's constant. Okay. Well, that again different investigator attempted in a different way. Different investigator attempted this in a different way. First, let me talk about this development by Horton and then Einstein. That is almost parallelly they did the study, and they went by the assumption that mean flow velocity in each of the sub area is equal to the mean flow velocity of the entire section. That was the assumption, and based on that assumption they derived one relation for equivalent roughness. Means when they calculate the mean flow velocity of the entire section, then they did use, say, equivalent Manning's constant. Well, what we can write, that means equivalent mean flow velocity, as we use that, say, V mean for the entire section, then we can write that V mean of the entire section, that we can write as 1 by NE, and then A by P, this is for the entire section I am writing, to the power 2 by 3, then S to the power half. Well, this S again we can consider, say, same for all the section. This S we can consider as same for all the means on the sub area here what is the bed slope, or here what is the friction slope, here what is the friction slope, and here what is the friction slope, that we can consider same. Okay. Then say we are starting from that, and then for the sub area when we write, this will be, say, 1 by Ni, then Ai by Pi to the power 2 by 3, S to the power half. Well, now by this assumption what we can write, by this assumption what can be written, that well, what can be written, that 1 by Ne into A by P to the power 2 by 3 S to the power half, that is equal to, this is the mean flow velocity, and that is the velocity, flow velocity of the sub area, that is, that we can write as 1 by Ni, then Ai by Pi to the power 2 by 3 and S to the power half, and in fact I can go for equal to 1 to m, any value. Well, now this can be written in a form that, well, let me rub this part. From this what we can do, say S being if I consider same, we can cancel it, and taking a power to 3 by 2, we can write that 1 by NE to the power 3 by 2, then we are writing this as A by P, and this is equal to 1 by Ni to the power 3 by 2, and then I am writing as Ai by Pi. Well, yes, I have already cancelled. And when we have a series like that, this is equal to that, then we can, if we take the summation of the numerator and denominator, then it becomes same. So we can write summation of Ai divided by summation of Ni to the power 3 by 2 into Pi. So that also can be written. And then simplifying that expression, what can be written? So combining this and that, we can write as, say, Ne is equal to summation of Pi Ni to the power 3 by 2. Then this P we can write also as summation of Pi. This can be written as summation of Pi, and then A and summation of Ai is same, so this will get cancelled, and we can write like that, summation of Pi, then enter to the power 2 by 3. So that way we get an expression for equivalent Ne. Then some other scientists, of course, did that, tried for getting the value of Ne, and suppose Lothar, he did this expression that discharge is equal to the sum of the discharge through the sub area. By following that, he got that Ne is equal to P perimeter, then R to the power 5 by 3, and summation of Pi, that is the perimeter of each individual, then Ri to the power 5 by 3 divided by Ni. So this is from that concept. Then again Malhofer in 1993, and Einstein and Banks, they also did in 1955. They were starting with the assumption that total resistance force is equal to sum of the resistance force of the sub area. And by this assumption, they could get the value that Ne is equal to summation of, say, Pi Ni square, and whole to the power half divided by summation of Pi to the power half. Well, so that can be one expression. Then Krishnamurti and Christensen. It is of course latest, but I mean it is not that most accurate. So in 1972, they derived by using that logarithmic velocity distribution. That means velocity distribution is considered as logarithmic, and that way they could get a value that log of Ne is equal to that summation of Pi Yi. Here Yi is basically nothing but the flow depth, and log of Ni, and divided by summation of Pi Yi to the power 3 by 2, where Yi is nothing but the flow depth. So that way different formula were developed, and but in 1980, in fact, a study was conducted with all these formula, and then it was found that the first formula what I have given, that gives in fact more accurate result as compared to others. So that way we can conclude that equivalent Manning's constant can be used for trapezoidal, for compound section, and then we have seen how we can carry out our computational work. Well, then with this we are concluding our discussion on the computation of open channel flow. Then we will be going for some more discussion when the channel carries sediment and other things. That is when the channel is erodible channel. That part we have not discussed. That we will be discussing in the next class. Thank you very much.